So next important question can be asked on the basis of Faraday's electromagnetic induction. So what Faraday's electromagnetic induction says is, whenever there is change in flux linked to a coil, EMF will be induced, and its formula is given by minus n d phi b by dt. Phi is the flux linked to the coil, magnetic flux linked to the coil. N is the number of turns. This negative sign shows that the induced EMF will be such that it opposes the cause producing it. So that is Lenge's law. Now question says, so how can you change the flux? By moving the bar magnet closer or away from it. So if you move closer, number of flux lines linked to the coil increases, hence EMF increases. And when you pull it away, so the flux changes again, and then EMF gets induced. Now the question says, can EMF be induced in a coil without any relative motion between the coils? So the answer is yes. So how to induce EMF without any relative motion between the coils? So the answer is, you can do experimental setup like this. When there will be two coils, they are coaxial to each other. Now you see, if you turn the switch on, current will start rising in this coil. When current will start rising, magnetic flux will gets produced, like using right hand thumb rule. The magnetic flux will get linked to the coil. As current is rising, flux will also rise. Change in flux with the link will also be there. So there will be induced EMF in this coil, and you will see deflection. Now after some time, the current will reach its maximum value and will remain constant in the coil. When current will remain constant, the flux linked to the coil will also remain constant. Now since the flux is constant, its change with respect to time will become 0, because differentiation of constant is 0. So there will not be any induced EMF in the coil. So when you turn the switch on, there will be deflection, and then quickly the current will come to become 0, because the maximum current here, the current reaches its maximum value, and the flux becomes constant and current becomes 0, induced current becomes 0. Now when you switch it off, the current will fall from maximum to 0. When the current is falling from maximum to 0, the flux linked with this coil also changing. So when the flux is changing, there will be induced EMF again, but the deflection in this case will be in the opposite direction. So yes, so you see, without any relative motion, but just by switching this circuit on and off, you can induce EMF. So in summary, what is happening? When you're turning the switch on, there is deflection, and immediately after sometimes the deflection comes to 0, because the flux is constant now. When you switch it off, there is deflection, and then immediately after that it comes to 0. So at the moment you turn it on and off, there is change in flux, and that is inducing EMF. So yes, it is possible to induce EMF without any relative motion between the coils. So another important question is, there is a series LCR circuit. RLC values are given, and it is connected to 220 volt of AC with 150 Hz frequency. What we need to find out: impedance of the circuit, peak value of current, and RMS value of current. We also have to find the power factor and calculate the power factor when the circuit is in resonance. So you know the condition of resonance is when maximum current flows through the circuit, and then impedance is lowest. So since you know the impedance of the circuit is of LCR is given by Z equal to R square plus chi C minus chi L whole square. What is chi C? 1 by omega C. Now omega, that means 1 by 2 pi FC. 1 by 2 pi frequency is 50 Hz, and C is 100 by pi. Pi gets cancelled, and you have 1 by 100 and 100, 10 to the power 4, that means 10 power minus 4 ohms. So unit of impedance is ohm. uh, so reactance for inductor is omega L. Omega is 2 pi f L. 2 pi into 50, L is to be 2 by 5. So 5, 10, so it becomes uh, 40, 40 pi ohms, right? So using these two values we can find out we can actually solve this pi 40 into 22 by 7, so it comes out to be 0.88 by 7 ohms. So the impedance Z will be given by R is also given, R is 100 ohm. So it is 100 ka square plus 10 to the power minus 4 minus 880 by 7 whole square. Alright. So when you solve this, okay, so here you see it is not just 100 by pi, it is 100 by pi minus 6 because it is microfarad. So it is 10 to the power minus 6, which becomes 10 to the power minus 2, and this will become 2. So it is 100, right? So when you solve this, 880 by 7 will give you how much? 180. How come? Okay, okay, okay. Oh, 700 minus. Okay, so it is 180 by 7 so square. So it becomes 180 square is 32400 divided 49 plus 100. So it will be 4900 32400 divided by 7 and its square root. So if you solve this, the value comes out to be 141 point. Actually in question it is printed as 2 by 5, but the actual value is 2 by pi. Alright, so there is correction. Value of inductance is 2 by 5. So if you take 2 by 5, omega L will become 2 by pi, then it is 50, pi gets cancelled, and you have 200 ohm, and that is 100 ohm, right? So the new value of impedance, now the thing gets simplified. The value of G now is 100 square plus 100 minus 200 whole square, which is 100 square plus 100 square, 100 root 2 ohms, which is 100 into, what is value of root 2? 141.4 ohm. So this is the value of impedance. So this is first part of your answer. Now you see the EMF is of 220 volts. So your VRMS is 220 volt. So what is V naught? VRMS into root 2. So it will be 220 into root 2 volt. So I naught will be V naught by Z. So V naught is 220 into root 2, and your G is 100 root 2. Root 2 gets cancelled. You have 2.2 ampere. Okay. Now you want to find IRMS. IRMS is how much? I naught by root 2. So it is 2.2 by root 2. You rationalize it. It becomes 1.1 into root 2, which is 1.1 into 1.414. So 341 it is 1.554 ampere. So you see IRMS is slightly less than I peak. You know the RMS value is almost 70% of the peak value. So if it is your current, this is your I naught, and this value is IRMS. So IRMS is almost 70% of I naught. All right. So we found out impedance of the circuit, peak value of current, and RMS value of current. Now we want to find out power factor and its value of power factor at resonance. So what is power factor? It is cos phi. So recall the impedance diagram. This is um, R, this is G, and this is chi c minus chi l, right? If this is phi, what will be cos phi? Base by hypotenuse, R by Z. So your value of R is 100 ohm, and what is value of impedance? 100 root 2. So 100 root 2, 100 gets cancelled. Cos phi is equal to 1 by root 2. What is phi? The power factor is 1 by root 2. Cos phi itself is power factor. And phase angle, if you want to find out, phase angle will be 45 degrees. This is power factor. Now we want to find out power factor at resonance. So what is resonance? At resonance, yes, chi c becomes chi l. So your impedance R square plus chi c minus chi l, this portion becomes 0. So it is just R. So impedance is just R. So cos phi, therefore power factor in this case will become R by Z, which is R by R, which is 1. So cos phi at resonance will be 1. So while power factor at the given case is 1 by root 2, at resonance it is always 1. So let me take this opportunity to explain you wattless current. What is wattless current? Current at which average power delivered is 0. So power factor cos phi becomes 0. That means phi will be 90 degree. This happens only in pure L or pure C circuits. So in pure inductive or pure capacitive circuit, power factor is always 0. Alright? Okay. Transformers, we'll see the important questions that can be generally asked in it, from transformers. The questions are: what are transformers? Does it follows the law of conservation of energy when step-up transformers is used? So what a step-up transformer does? Transformer is a device that converts a low input voltage to high output voltage, and vice versa. So given a low input voltage, it will get converted to high output. How it does? So there are two coils, a primary coil and a secondary coil. The flux gets linked to the secondary coil, and there is large number of turns in the secondary coil, so flux gets increased and then output gets increased as per Faraday's law of electromagnetic induction. Similarly, for step down transformer, it lowers the output potential by decreasing the flux, total number of flux. So the transformer actually do not violates the law of conservation of energy, as total input power is always equal to total output power. So how the potential gets increased? So there is trade-off between the potential and current. If you increase potential, there will be decrease in current. So you see this relation. Input power is constant, output power is also constant, same. If you increase output potential, current should fall to keep the potential constant, right? For example, let us take an example. If IP is 10 ampere, VP is 10 volt, and Vs is 20 volt, so your Is will be 10 into 10 by 20, which is 5 ampere. So you see, if you are increasing potential, current falls proportionately to maintain the constant potential, constant power. So it follows the law of conservation of energy. There is no violation. All right. So yeah, in step-up transformer, the increasing potential is compensated by low current, proportionately low current. Another important question is why power is transmitted at high voltage and not at high current from power plants. So it has to do with resistive losses. To avoid resistive losses, so as the power is transmitted, the wire has got resistance. The power loss is directly proportional to the square of the current, and it is also directly proportional to to just the potential. So if high current is used, power will be lost quadratically, but if high voltage is used, it will be linearly lost. So quadratic loss is much greater than linear loss, so power is generally sent at high potential rather than at high current. All right, the next question from transformer is related to power loss and transmission related question. So it says a town is situated 20 km away from power station. Power station is generating power at 440 volt. This town requires 600 kilowatt of power at 200 volt. Now the resistance of the two wire, the power is transmitted through two wire. Resistance is 0.4 ohm per kilometer. Now the transformer gets power through 3220 volt step down transformer. So here you have 3000 to 220 volt step down transformer. Now we need to find out how much power is lost during transmission, and how much the power plant must supply so that the town receives 600 kilowatt of net power. We need to assume that there is no further leakage in power during transmission. There is just pure resistive loss. That's it. Now to solve it, we have to find the total resistance of the wire. There are two resistance 20 km away, so total length of the wire is 20 into 2 equal to 40 km. Now total resistance, what will be total resistance? 40 kilometer into 0.4 ohms per kilometer. Kilometer gets cancelled, so you have 16 ohms. Yeah, total resistance is 16 ohm. Now, no, total resistance of the wire is 0.4 ohms per kilometer. So for 40 kilometer, you multiply it by 40 kilometer, you get 16 ohm. So total resistance of the wire is 16 ohm. Now we'll find out how much current is flowing in the circuit. So the requirement here is 6000, I equal to, P equal to VI. So I will be P by V. P power, how much power it requires? 600 kilo ohm, that means kilowatt. And your potential is how much? 3000 volt. So if you solve it, it is 200 ampere. Therefore, power loss will be I square R. So it will be 200 square into what is resistance of the wire? 16. So it will be into 16. So it will be 640 kilowatts. So this is 1000. So 16 into 40 will be 640 kilowatts. So this is the power which gets lost while delivering. So you see, the town requires 600 kilowatt and more than that is getting lost, wasted. So there is huge wastage. All right, so next part, how much power must the plant supply? So the power supply will be power demand plus power loss. Demand is 600 kilowatt, loss is 640 kilowatt. So total is 1240 kilowatts. So this is total supply that must be given by the power plant. Okay. Move to other equally important question from electromagnetic wave. The question is how an EM wave is produced. The answer is the accelerating charge particle will create electromagnetic wave. You know, any accelerating charge particle creates electromagnetic waves. For example, you know, electrons, high energy electrons are moved and struck on a wall, you know, and when they stop, the speed, you know, retards and the electrons comes to rest, and that's how X-rays are produced. So you must have heard sound of like this when X-rays are, you know, splashed on someone. Now the other question, equation of electric component of an EM wave is given. You need to find equation for magnetic field or the magnetic component. Now, you know, magnetic, so we have equation of electric component. Electric component will be given by E equal to E naught sine kx minus omega t j. So comparing this equation with the given equation, E naught comes out to be 4 into 10 to the power 6 Newton per Coulomb. What is K? K is 100 meter inverse. And what is omega? 37 radian per second. Now, since we know that B naught is given by E naught by C, so E naught is 4 into 10 power 6, but C is 3 into 10 power 6, 10 power 8 meter per second. So if you solve it, it comes out to be 1.33 10 power minus 2 Tesla. So equation of magnetic field will be, see, electric component is oscillating in J direction, that means Y axis. It is oscillating along Y axis. Wave is propagating along positive X direction. So the argument tells you about the direction of propagation of wave. So wave is going along positive X axis. Had this been positive, the wave would have propagated along negative X direction. So the wave is propagating along positive X direction, and this is your peak value of electric component. Electric component is oscillating along uh, Y axis. So naturally, since you know, if wave is propagating along this direction and electric component is, if this is X, Y, Z, so this is your electric component because it is oscillating along Y axis. Your magnetic component will then be along Z axis because wave is propagating along X axis, electric component is along Y axis, this is E naught, so this will be your magnetic component. because waves are perpendicular to each other. The electric component and magnetic components are perpendicular to each other. So B will be B naught sine kx minus omega t into k, because it should be along z axis. So B naught, we already have calculated B naught, so 1.33 10 to the power minus 2 Tesla, and you have the same value for argument, so you get 100x minus 37t to k. So this is the required equation for magnetic component. Next part is direction of propagation of wave. Clearly the wave is propagating along, the EM wave is propagating along positive x-axis. Wavelength, k is equal to 100 meter inverse, so k is 2 pi by lambda 100 meter inverse. You see, this is kx, so k is 100. We have found out the value of k, 100 meter inverse. So k wave number is 2 pi by lambda, so lambda will become 2 pi minus 100 meter. So 2 into 3.14 by 100, 6.28 by 100, so it becomes 6.28 into 10 power minus 2 meter. So this is the wavelength of the electromagnetic wave. Fourth part is frequency of the EM wave. So we have omega is equal to 37 radian per second. So 2 pi into frequency, 37 radian per second. So frequency will become 37 by 2 pi hertz or second inverse. So you can solve it, 37 by 2 into 22 by 7. So it becomes 2 into 2, 2 8 is 16, 5, 11, 2 9, 2 5. If you solve by 11, 11 8 is 88, 4, 11 4 is 44 into 7. So it is 5.88 hertz. So required frequency is 5.88 hertz. So that's how you solve such questions. Another question from this can be, write down uses of EM wave. So the EM waves have gamma, X-ray, ultraviolet, visible, infrared, microwave wave, and radio wave. So if you go up, frequency rises, energy also rises. So highest frequency, highest energy wavelength is gamma, and if you go downwards, wavelength increases. Gamma rays are used for cancer treatment, X-rays for medical
cancer
examination,
for detecting fractures.
For detecting fracture. Ultraviolet is for sanitation. You have ultraviolet,
Imitation or jump.
germ cleaning. So you have UV RO. Most of the people have UV RO. This is visible, which helps us see the colorful world. So its wavelength is 4,000.
4 angstrom to 7,000.
7,000 angstrom. This is important. You should keep in mind. Infrared is for heat sensor
or night vision device.
and night vision device.
And microwaves.
Microwave is the most important portion is
navigation.
yes, airplane navigation.
एक और होता है ना सर इसका.
Nowadays it is being used in 5G communication. Radio is for communication.
Radar system.
Modi ji does Man Ki Baat on radio, so yeah. So because this is cheapest source of communication, cheapest, and can reach everywhere efficiently.
FMEM, this is AU.
All right. So the next question is, what are displacement current? Find it for phi e is equal to 1 by epsilon naught t cube 3t square plus 37t at t equal to 1 second. So first you need to tell what are displacement current, and you have to find displacement current for this electric flux. So displacement currents are the current which flows when there is change in electric field or electric flux. So when there is change in electric flux, displacement currents are flowed. So displacement current ID is given by epsilon naught d phi e by dt. It flows in capacitors. See, if you have a capacitor, you see that this medium is empty, but still the current is flowing. Current can't flow through air, but here you see, since charges are getting increased, there is change in electric field. This change in electric field changes electric flux. In turn, and displacement current flows through this air via these electric fields. So electric fields are the carrier of displacement current. Now, so to find displacement current, we have to differentiate this electric flux which is given. If you differentiate, this epsilon gets cancelled. You have 3t square minus 6t plus 37. So displacement current at t equal to 1 second, you put t equal to 1, it becomes 3 minus 6 plus 37 amperes, which becomes 34 ampere. One should keep in mind that displacement current which flows through the air is same as conduction current, because total charge is conserved. The charge which is flowing in this direction also travels through the air and comes to the wire. The current which flows through the wire is conduction current, and the current which flows through the air via electric field is known as displacement current.
So E naught